All right. Well, this is a brown bag session about creating a snapshot and feedback-based fuzzer. And yeah, we will go pretty technical, have a fair amount to cover in less than an hour. So if you have any questions, please bring them up while we're talking, and then uh, I can condense or expand content as I need to. Uh, if I wait till the end, I'm afraid nobody will have time for questions. All right, I'm going to share my screen and we will get going. All right. So I am James Johnson. I am a staff security engineer on the vulnerability research team at GitLab. And a lot of my background has to do with fuzzing. It's something I find really fun to develop tools for. You get tossed into a lot of interesting situations, problems to solve, and yeah, it's just interesting to me. And I have done it a lot at past jobs. And this is a link to all of the example material in the slides. So if you wanted to, you could follow along and download everything and run it yourself while we talk about it. Let's see, I can paste this into chat as well. There we go. All right. So this is what we will be talking about today. So we'll start at pretty relatively high level with debugging, talk about what we want to cover, why we want debugging, what the types of information we might want to capture. And then we'll cover mutation, snapshots, feedback, and then we'll touch briefly on using a corpus of inputs for fuzzing. All right, so you could call this a very basic debugger. It's a bash script, and oh, here we go. That's better. All right, it runs a process, you get the exit code, and if the exit code isn't 0, it isn't successful, you could say crashed. It operated in a way that wasn't intended. But you have no idea what's going on, and bash, I will say, is probably not the best way to implement a fuzzer or a debugger. So here's roughly the same thing, except written in Rust. So a lot of the source code in this is in Rust. It's something that I've enjoyed learning. I don't really use it much here at GitLab, but a lot of the source material and research for this presentation comes from some things that I've done on the side, and just for fun programming, and that has been in Rust. So it's been easiest to do a lot of the code in this presentation in Rust. So yeah, but this is doing pretty much the same thing. It spawns a new process, checks to see if it's successful. If it's not successful, we'll say it crashed. All right, so if we are going to test a debugger, it is often most useful to have a known crashing program so that you can test things out. So the first example is this target simple.c. It has one function. It has a main function that calls this function. And if the data passed to this function is GitLab, then it crashes. And this is a null pointer dereference. We're trying to write the character A to the address 0, which will fail. All right, so if we run this locally, you can just compile it with GCC or Clang if you want, and you run it like so. We'll see, oh, oops, I did not have, oh, here we go. We'll see something like this. We'll see a seg fault, and if we check the status or the exit code of the process that we just ran, it is non-zero. So our basic bash or super basic Rust debugger, we will see something. It didn't exit cleanly. Let's go back though. And this is, all right, this, what was that? Actually, yeah, that slide didn't need to be there. But we need more than this. This isn't enough information to really have a robust debugger and to figure out what's going on or if the crash was interesting. So just looking at the output from here, we can tell that the exit code was 139 but we don't really know much else. We know this is the code that caused the crash. We wrote it, it's very simple. But we don't really know much more besides it had a non-zero exit code, and we know the exit code was 139. So we need more information. So if we run the same target simple binary with GDB, we'll see we have a seg fault. We have a signal, sig-seg-v, which means it's a segmentation fault. And so that's, now we have the name of a signal that we are capturing with GDB. Now, we're not going to automate GDB. In the past, I've done that type of debugging quite a bit, where I just wrap an existing debugger. I've used that a lot from Python, both on Windows and on Linux. I've written generic debugger wrappers that wrap either GDB or CDB, so command line WinDebug. And it works pretty well, but for really fast, kind of higher performance fuzzing, it does not work that well. And when I was using it, it was mostly for things like Adobe Reader, browsers, that type of thing. Your performance on those is pretty small anyways. All right, so let's talk briefly about signals. So this seg fault or segmentation, what was the full? Yeah, it's just segmentation fault. I'm not sure what the V stands for, but the seg fault signal is sent by the kernel when memory errors occur. And you can think of signals as they're similar in the same way that interrupts relate to kernels and hardware, signals relate to processes and the kernel. So with hardware, an interrupt can be sent to the kernel that absolutely needs to be handled. If it isn't handled, then the computer itself will just crash. The same relationship exists with processes and signals. The kernel can send a signal to a process, and the process may handle it or not. That is one of the big differences, is that most handlers are optional or they have default actions. So sig kill and sig stop can't be handled though. If that is sent to a process, the process just dies. There's no way to stop it. All right, so let's go through a few more examples of contrived crashes in programs, just so that we can look at the signals they generate. Now this one is a double free. We allocate some data and we free it twice in a row. This does come up in complicated C-based languages. You can have double frees. And this does not generate a seg fault. You have a sig abort. So a little slightly different behavior. So if we are looking at trying to glean as much information as we can from the target as it's running, knowing which signal was sent to the process can be very useful, or more useful than not having it. Let me say that. All right, so let's look at another one. This is a stack overflow. So we're not overflowing a buffer, just a stack overflow, infinite recursion. We run out of stack space. This one is also a seg fault. And again, we're doing the same thing. We compile it and we run it with GDB so we can see this signal. And here's another one. This one is a little more interesting. This one I have seen this before, especially with if you're fuzzing a target that has some aspect of JIT to it, you can have it execute invalid instructions. Or if you have a use after free and you make the instruction pointer jump to some random place in memory that happens to be executable, you can see this error, an invalid instruction. So a 90 is a NOP, and so that's here. And then CC is int3, and then NOP int3. And this one, 6, is an invalid instruction on x64. And so what I'm doing here is I allocate some data, I set it to be read, write, execute, and then I cast that data location to be a function, a callback, and then I call it to make the instruction pointer go to that data. Then we start executing these raw opcodes directly. And this is where it crashes. This also happens to be a seg fault. All right, and this is actually the full list of signals. One of the ones that I recently had to deal with was It's not going away. All the way at the bottom, there's sig winch, and I'm pretty sure it means window change. So when the window resizes, that signal is sent to the program. So if you are just generically capturing all signals sent to the process, and I actually haven't fixed this in the code. So if you run the sample fuzzers in the examples directory, if you resize the terminal window, it will think a sig winch signal is a crash. So yeah, there's a lot of signals going on, and it's kind of interesting having that insight into what's happening with the process. All right, so so we've got signals, we know the exit code, but we really want more information than that. So next up, we really need to have our own debugger. On Linux, this is where I would start using ptrace, and that's what we'll be talking about. We can use this to fully debug and control a process. We can read and write registers. We can look at the process state, read memory from it, change register values, monitor the signals, everything. And actually, this is what GDB uses ptrace. All right, and so I'll be quoting the man pages a lot in here. They're very succinct, clear definitions about what all these functions are. So ptrace, there's a ptrace function, and you send it a request, and the request values like ptrace trace me are the main way to use ptrace. So the way you start using ptrace is you have a child process. In the child process, you have to call ptrace with the request ptrace trace me. Once that is done, then you can start debugging the process and tracing it. So in the examples directory, there's the B spawn with ptrace, very similar to the A example. And here we are doing exactly what I said. So we spawn a new process, and that's what we're doing here. When the process is spawned, it's initially stopped, and so we execute some code first in that context, and that's where we do the ptrace trace me request. And then after that is done, the process is created, then we have the child PID, and then we wait for the PID and make sure it is stopped. And once we hit this point, then we just continue the process and the process continues running. How are we doing on time? Okay, we're doing just fine. All right, so if we run this with each of the different processes, we can see, or each of the different example targets that crash in different ways, we can see that we are capturing the different signals. So all of them are seg faults except for the double free, which is the sig abort. So yeah, our debugger is working. So knowing the signal still isn't enough, but we want the registers, we can also look at the last instruction. We can start analyzing the stack and the heap. Having a debugger in place where you can actively inspect a process is very critical in automating this type of thing. All right, so another way that we can gain additional information about how a process is crashing or how these errors are occurring is using sanitizers and Clang. So sanitizers are, so Clang is part of the LLVM project, and part of how the LLVM project works is it takes source input and transforms it into LLVM's intermediate language, so LLVM IR. And then transformations are performed on top of the IR. And then at that point, or after that, then the IR is transformed to architecture-specific machine code. So the sanitizers operate on the IR, and they insert instrumentation in different ways so that we can get extra feedback about how things are occurring. So we may get more insight into how something crashed, but it can also ensure that things do crash when they go wrong. So certain types of errors, like use after free is a good one. If you're not running with one of the sanitizers, you could free an object and the memory of the freed object is still floating around on the heap. It isn't cleared out. So if you have a stale pointer pointing to this freed object, you could still use it. It may have been overwritten by something else or partially overwritten. And then when that stale pointer is actually used, it is going to use a corrupted object. So what some of the sanitizers add checks into the code at compile time to make sure that never happens. It will crash if there is ever a use after free. So here's a list of some of the main sanitizers. There are a few other ones I'm not that familiar with. The most important or most used ones to me are address sanitizer. That's the one I pretty much always use. There's also memory sanitizer, detects use of uninitialized memory. So address sanitizer is, I think I quoted on the, oh, I didn't add it. All right. So address sanitizer itself is pretty interesting. It does operate on the code at compile time. And if I remember correctly, every heap allocation gets its own page in memory. So that way, if anything is read beyond the scope of the allocation, then it causes a crash. So if you allocate a buffer on the heap and you try to read beyond the bounds of the buffer or write, it crashes. All right, and using sanitizers is pretty straightforward. If you've never used Clang, just think of it as another version of GCC, something that knows how to compile C code. So use it like normal, but you add this -f sanitize equals then the name of the sanitizer. So if you want to compile the example targets with this is a command line you could use. So the double free address sanitizer will output additional information and context into why something crashed. And we'll go through the different sample or contrived targets and how they look with address sanitizer. All right, and this one is the Stack Overflow. It does give you very nice error messages saying a little more clearly exactly what happened, and maybe a little more context about what caused it. And so this one is the very basic one with that crashes if you give it GitLab and it tries to dereference null. So here we go, a hint, address points to the 0 page. So signal is caused by a write memory access. So you know it's not because you're trying to read from somewhere that doesn't exist, you're trying to write there, and it's the 0 page. So to summarize so far, we can launch a process and we can monitor it and debug the process. We can use sanitizers, but now we need to actually start sending inputs to the target process. All right, so with mutation, we'll keep it pretty straightforward. We will just mutate random bytes in existing data. We're not going to worry about changing the size of the data being sent or anything. So, and here's example C. It's another Rust project. This takes an existing array of bytes. So U8 is just a character, a byte, and it's a vector, it's an array. So we take that and a random object. This knows how to generate random numbers. So n number of bytes, or for n number of bytes, or n number of times, we choose a random index and we set it to some random value in the character set. And that's it. Very simple mutation. And here we are in the main function actually using it. So we are spawning the process every single time. And so we have this scratch buffer that we just keep reusing, we keep overriding. So we copy the original input in, and then we mutate this scratch buffer, again, passing in the rand object and the scratch-based buffer, and then we spawn the process. And then we monitor it to see if there's any, to see how it crashed. And now this, I let it run for a while, and it never found GitLab. Yeah, it just never found it. So, and that's actually expected. So we've got 6 characters here. So if we do 1, 2, 3, 4, 5, 6. That many options to or 1 in that number are the odds of finding the right, randomly generating the correct value. And actually, it'd be a little higher because we're not generating 6 bytes every single time. We're generating a random number of bytes or mutating a random number of bytes. So the odds are even lower that we will find GitLab with this method. All right, so moving on to the next phase, snapshotting. It's a little bit of a gear shift, but why would we want to snapshot? So process creation is very slow. If we are creating a new process every single time, that's a lot of setup time and teardown time for that process. One of the other benefits of snapshot fuzzing is that the program itself may have a long setup time before you even get to the interesting code. So if you are using a snapshot-based fuzzer, you could potentially take a snapshot after all the setup has occurred, and then you fuzz only the interesting part. And you also have options to make it more deterministic. It's not always the case, but that is something that applies in general to the concept of snapshot-based fuzzing. It can be more deterministic. Actually, let's go back to this and look at the iterations per second. So creating a new process every single time, we're getting about 700 iterations per second. So it's faster than some other things, but in general, that's not too fast. All right, we're doing good. And so what does a snapshot actually mean? To me, it means you're recording the state and restoring it. It should be that straightforward. It does get a bit complex, and there are shortcuts you can take. You don't have to do the full thing, but if you're fuzzing or wanting to snapshot really complicated targets, it gets a lot more complicated than that. So these are some of the things you might want to record and then restore. So the memory of the process. If you take a snapshot and then the process starts allocating things on the heap, starts making state changes on the stack or in wherever, you are going to want to be able to reset all of those changes back to their original state when you took the snapshot. So register values. There are standard and floating point registers. You need to snapshot both of those sets and save them so that they can be restored. File descriptors. So let's say a process has 10 files open. How are you going to handle those? Let's say you snapshot the process and you continue doing the fuzzing. It closes 5 of the file handles. How do you restore it back to its original state? Or let's say that a file was immapped into memory, or there's existing immaps that were then closed. How do you deal with those types of things? It does get very complicated. If for the examples in this presentation, we won't deal with file descriptors or network sockets or immap data. We're really only going to focus on memory and register values. But the other ones are definitely things to think about. All right, so Procfs. Procfs is it's a pseudo file system, and it gives you access to kernel data structures. It's not the fastest thing in the world, but it does give you the information you might need if you're going to do implement some sort of snapshot system. So in general, Procfs is our friend, but really it's our frenemy. We like it because it gives us the information we need, but we actually really don't like it. And there's reasons for that. We'll get to those later though. So here's some important Procfs files for snapshotting. There's proc maps. Oh, and for each of these, if you want to test them out or look at them on your system, if you go to proc/self/ then the file name, that refers to the current process. So you could do proc self maps, and that will be the maps file for that process. All right, so first off, procpid maps. It contains a list of all of the mapped regions for that process. So a region is different than a page. When you mmap something, it shows up as a new region. The stack has its own region. Each of the binaries or libraries loaded into memory lives in its own region. So if you cat proc self maps, you'll see something like this. And you can see user bin cat is actually loaded multiple times with different sets of permissions. And I'm not going to go into that, but this is really interesting to look at and to kind of get a feel or understanding for what's going on in the kernel when a process runs. But down here, you can actually see this is the stack region. So as functions are called, they leave stack frames on the stack. The stack would definitely be a memory region that you would want to restore. So if you're thinking about snapshotting, this gives you a lot of information. You can probably see ways where you don't need to capture all of this stuff in memory so that you can restore it. If you can't write to it, it's probably never going to change. So maybe you don't need to save it, for example. All right, so this one is another interesting file. This is the memory of the process. It's not actually just a file with all of the process's memory. Remember, these are, it's an interface to kernel data structures. So if you open proc and then the PID and then mem and seek to an address in memory, so let's say you know of an address in a process and you want to read that value using the mem procfs file. You would open it, seek to the address, and then read however many bytes, and that would be the memory from that process. And one of the examples in the examples directory is procfs read mem.c, and this does exactly that. And this is what it looks like. Here we go. We're reading proc self mem, and this will always be the current PID. So it's very handy that way. And then we seek to the address of this data variable here, or data pointer. And here we're going to create, allocate some new data. And again, we're going to allocate the data, and then we're going to read from proc mem the length of data. And then we're just going to print the result. So what should occur is that we will print out hello world, but except it will be from new data, and that will be a value that we read through procfs, through the mem file in procfs. And that's exactly what happens. So I don't know why you would actually want to do that. Maybe there's reasons, but for normal programming, I've never needed to do that. Maybe for some anti-cheat types of things, having an outsider's perspective of your own process could be interesting. All right, so clear refs. So if we go back to this is a lot of data that's loaded into memory. These regions can be fairly large. And so if we're restoring each of these every single iteration during fuzzing, that's going to be a serious bottleneck. So keep that in mind as we go through these next steps. So clearrefs, it's a write-only file. Again, you're setting some value in kernel memory. You're accessing kernel data structures through procfs. And what this does is it clears all of the dirty flags on all of the pages for the process. So what you can do with this is clear when we look at the next one, page map. So the page map gives you, so there's a 64-bit value in this file for every single page loaded in, into the process. And the 55th bit of that value for each page in the process's memory indicates whether or not that page is dirty since the last time clearrefs was written to. So now we have, if we write the value 4 here to proc clearrefs, all of those dirty bits will be cleared. And then if we let it run for a little bit, and then we check these values in page map for every page in the process, we'll know which pages in memory have been changed since we wrote to clearrefs. So this actually did originate from the checkpoint restore project. It's criu.org. So that's where this concept originated, and it was created in order to do snapshotting or to make that easier. And it is actually used a lot with Docker containers. Yeah, there's a lot of research around how this applies to Docker. All right, so, but why do we really care why they are dirty? It's pretty much performance. If we only have to restore one page in memory versus all of the regions that we know about for the process, things will be much faster. Also, if we're operating on x64, the address space here is incredibly huge, and we do not want to be trying to save all of the process's possible memory for every snapshot. All right. Now remember, Procfs is our frenemy. It's not our friend. It's useful, but it's very, very slow. So this, this is his handle, I think, but his blog talks about how Procfs is not that fast. And he had a fork of the Linux kernel that was trying to do, let's see, change the APIs for accessing those kernel data structures. Instead of using a file-based system where you have to use multiple syscalls just to get at the data, his branch of the, or fork of the Linux kernel was using a different method in an effort to speed it up. And if you search around, you'll see a lot of links talking about how Procfs is really not that fast. And we'll talk a little bit more about that on these slides. So reading and writing memory from proc-mem requires a few syscalls. You have to open the file, you have to seek, and then you have to read or write the values, and then you have to close the file. So now you could leave the file descriptor open, and then you just seek and read or write as you want, and then close it when you're done. So you could kind of rule out the first two, but even then, for every single value you want to grab from the process's memory, you have to do two syscalls at least. You have to seek and you have to do the operation. So there are better APIs for doing this type of thing. So there's process VM write-v and also read-v. These both take an array or two arrays of local, or not local, two arrays of IO vectors is what they're called. So there's the local IO vector and the remote IO vector. And they're arrays that indicate what data to write, that's a local IO vector, and then where to write it to. So you can pass a whole list of data and address pairs. You can send those lists to process VM write-v, and it will do all of them in one syscall. And actually, it's not using system calls. I actually thought it was. But it does it all in one shot instead of having to do two syscalls for every operation. And it's the inverse for read-v. So you have an array of buffers with known sizes that data from the remote process is going to be read into, and then you have an array of addresses in the remote process that indicate where the data will be read from. All right, so we have a lot of the building blocks in place. Now let's start putting them a bit more together. So we have, if we want to record a snapshot, the process must be stopped, and we need to record the registers, and these have to do with ptrace. And then with Procfs and the process VM functions, we need to copy all of the writable regions indicated in the maps, and then we write for to clear refs. And so that will clear the dirty bit flag on all of the pages in the process's memory. That way, when we go to restoring the snapshot, again, the process must be stopped. We restore all of the registers that we saved, and then we check the dirty bit for every page in the process. And if it was dirty, then we restore all of the dirty pages with process VM write-v in one shot. And I mentioned this before, this does ignore all of these things. I didn't mention child processes. What if it spawned a child process and we're resetting things? If your target is, the target that you're fuzzing is very complex, you will probably have to deal with these and figure out how you want to approach it. Maybe it's fine to, when you restore it, to just kill all the child processes that didn't exist at the time when the snapshot was taken. Maybe that's all you need to do. But you still have to deal with multiple threads, memory mapped regions, new file descriptors that were open, lots to consider. All right, so snapshotting is super useful. There is a lot of research going on in that realm, and I did not add a link to something else that I want to. So AFL, it's a very popular fuzzer. There's AFL++. Some of the AFL++ guys have been working on this AFL snapshot Linux kernel module that takes care of all of the snapshotting on the kernel side, so that you can have high performance snapshot-based fuzzing without having to do multiple syscalls. Oh, one of the other things I was going to mention here is that there is also research going on in doing emulated fuzzing, where you emulate a different architecture, possibly a simpler architecture in memory. And in the emulator, you have full insight into everything that's going on in the process, or whatever you're emulating. So you're able to capture everything you need to without needing to do anything with the kernel. It's been emulated, so you have absolute control over everything. And that's another very interesting area with snapshot fuzzing. So now that we know how to make the snapshots, let's make a better target. All right, so we have in the examples directory target with breakpoints.c, and this source code here, I took out all of the breakpoints to talk specifically about the slow setup that I added. So the main function calls do something, and this intentionally takes maybe a second, or maybe a little less. So if you were to fuzz this program end to end, you would not have a fast loop that you're iterating through. You would have like 5 iterations per second or something. We are, all right. So if we look back at, not that one. I meant to include this on this other slide. Okay. So this data is coming directly from the command line of the process. And I'm realizing I did not put the screenshot that I wanted to show in there. All right, so let's go back to here. So we've changed the target process to have a slow section with the interesting bit coming after the slow section. And the data that is being provided to the program just comes from a command line argument. Now, if we're using a snapshot-based system, we'll create the process once and then keep resetting it. So how do we modify that input value on the command line? And that's what we're talking about next. So we can manually insert breakpoints. The intention here is that you could have an automated way to find these locations that you want to breakpoint. And I'll talk about some of the ideas on that in a little bit. But in general, the example fuzzers work like this. It flags the data that will be fuzzed, and then it triggers the snapshot, when to take it, and then it triggers the snapshot restoring. So the target itself has been manually instrumented to have these interactions with the fuzzer. So this is how we're flagging the data inside the target process. We're using some raw assembly, and we are triggering an int3 that generates a sig trap signal. But before that occurs, we are putting a special value into RCX, so food feed. If the fuzzer sees food feed, then we know that that sig trap is at the location where the memory address was tagged. And then when that happens, then we grab RAX from the registers, and RBX indicates the size of the data. And now we know the address in the target process and the length of the data that will be fuzzed. And something else here you might notice at the bottom, we say set watch point, and that is what we do on the next slide. So taking the snapshot, this is actually setting the watch point or a hardware breakpoint. That is done on the address of the data to be fuzzed. So in the target process, the argv1 is passed in, and that gets put into RAX, which becomes this overwrite data address, right? And then we set a watch point on it. So the next time that data address is accessed, then a SIG trap will be triggered or sent to the process. And what that gets us is we don't need to manually figure out the best place where, let's see. What that gets us is we don't need to manually insert the breakpoint to trigger the fuzzing. So now we take the snapshot as soon as the data of interest or the input to the program is actually used. And in this contrived example, that gets us past that slow section. And where that actually takes us is, let's go all the way back to here. One more. All right, so where that actually takes us is inside of stir length. This is the first time the data is accessed, and that's where the hardware breakpoint triggers the SIG trap. And at that point, that is where the snapshot is taken. And this is completely after the slow section. And during the development of the snapshot fuzzer code that I did in my free time, I actually had a problem where I wasn't saving the floating point registers. So a lot of the string functions in the standard library use floating point registers to increase performance, right? And I wasn't saving those when I was doing the snapshotting, and I kept it kept crashing sometimes here inside of Sterling after I restored it. And it took me a while to realize that I wasn't restoring the floating point registers because those are what Sterling was actually using. All right. Okay, so we have the hardware breakpoint. That gets us, it sends a SIG trap inside of the Sterling function. And that's the point at which the snapshot is taken. So at this point, we need to, actually, that's right. This slide is talking about specifically how the hardware breakpoint is set. It's pretty interesting. We are starting to run out of time, so I'm going to kind of gloss over it a little bit. But there's debug registers on Intel processors, and DR0, 1, 2, and 3 are each track a specific location in memory that can be set. So you can have 4 hardware breakpoints going at a time with those 4 registers. The DR7 register is a debug control register, and you set values inside of that register to enable or disable each of these DR0, 1, 2, or 3 registers. It's a little more complicated than that, but that's the gist of it. And you set these registers specifically with ptrace poke user. You can't use the normal getregs request. All right, so restoring the snapshot, there's another breakpoint triggered at the end of the target program, and this is watched for in the fuzzer. If a SIG trap occurs after we've already started the fuzzing loop, then we know it's ours, and then we just break. Now, really, a SIG trap could occur in the process. Maybe the developers of an actual real application have an assert that they left in that would trigger a SIG trap. More logic would need to be added here to handle that type of thing. All right, so if we run this, we'll see that we receive the tag memory address, and we have the max data length, and we have the address of the data to be fuzzed. And here, this is the watch point or the hardware breakpoint being hit. This is inside of the stir length function. And so we took the new snapshot and we copy all of the writable regions from memory, and then we start the fuzzing loop. So at the start of every fuzzing iteration, we restore the snapshot, and then do the fuzzing. And this thing keeps showing up. But if we look at this, we're getting 32,000 iterations per second. If you remember, when we were creating a new process for every iteration, we were only getting 600 iterations per second. So snapshot fuzzing does have huge potential. And it's really not so much the snapshotting that is getting us this performance. It's that we're not creating a new process every time. And there are other techniques to not create a new process every iteration. But in this case, since we aren't creating the processes every time, we also get that benefit with snapshot-based fuzzing. But if you look at this, we have, what, 18 million iterations, and it never triggered the correct value. We're just randomly mutating data, random number of bytes every time, and we still haven't hit it, even with a much greater speed. All right. Let's see. So let's say if we're generating inputs to send to the program, some inputs will be more interesting than others. The general theory behind a corpus is that interesting inputs will need to be tracked and maybe prioritized based on how interesting they are. And non-interesting inputs, maybe ones that you've seen before, will just be discarded. And so this corpuses work hand in hand with a feedback metric or a fitness function. And here, this is all I need for a corpus. I just need a hash set to know if I've seen some feedback metric or not, and a list of the items that I have seen first and that I care about. In the example code, I'm prioritizing the last half of the items, or the most recent half of the items that I've seen. That is some way of saying the most recent ones are the most interesting because they've made it furthest into the program. All right, usually using feedback in a fuzzer looks something like this. You might revert the snapshot, start recording, whatever that means to the type of feedback, run the target, and then you get your metrics from the feedback. And then you check in the corpus if you've seen that feedback metric or not, and decide if you want to save that input. So types of feedback. Coverage is the obvious one, but there are other ones. Performance counters, manual breakpoints, anything meaningful that can indicate progress in the fuzzing process. So coverage is the default. Clang supports coverage as a sanitizer. So it gets inserted into the code at compile time, and you can access those coverage metrics except you directly in your fuzzer, except you have to know about it and you have to access them. So you need to read the Clang documentation to be able to work with the Clang sanitized coverage sanitizer. The feedback metric that I'm using in these examples is actually performance counters. It was very interesting to me, and that's why I used it. It was different, and I wanted to use a different feedback than coverage, because coverage is what everything uses, and I wanted to see if something like this would even work. So these are all of the types of performance counters that are tracked by the perf Linux subsystem. There's quite a bit, and these are for the user or system-wide as the kernel. You can specify what type of counter you want to have for each of these. Part of the problem with using performance counters is that they are non-deterministic. The perf subsystem is sample-based, so it will record samples of each of these counters throughout the recording process. So 2 consecutive runs of a program will end up with different counter values. So if we run these, this instruction or this command, and all we're doing is echoing hello, and we're recording the number of cycles, number of instructions, and bus cycles, right? Could have added branches in there too. So this is 1 and 2. They have pretty largely different numbers on these. Now, does that matter actually? And it actually turns out it doesn't matter, or not as much as you might think it does. So cycles definitely matters. There's a huge variance in cycles, like 4,000 different instructions is a lot fewer. Branches is actually very few. So if you use performance counters that don't change too much, even though it's non-deterministic, it still works just fine. And actually, I think it might even help the process. Adding some jitter to the feedback will cause you to save extra inputs that are interesting just because of the jitter, but that could help you in the fuzzing process to not give up on certain paths too early. All right, so this is an example. This is the side project that kind of spawned all of this for me, of doing snapshot-based fuzzing in Rust with performance counters. So resmack fuzz test, I call the fuzzer resmack, and this is just my experimental fuzzer for that. So this is that running on a target. It's pretty much identical setup, except it's looking for the words resmack. And this is the full thing working with perf counters as its feedback mechanism. So if you remember, we had run 18 million iterations with the snapshot-based fuzzer, and we still didn't see the crash. This is looking for an even longer input, and we get the crash in about 60 or 70,000 iterations. So it took like 2 seconds to find it, and then we got it. Now, we are very, very close to being out of time. Does anybody have questions? I've got 2 slides left. So think of your questions. I'll cover these real quick. So perf-events definitely has pros and cons. Some huge pros is that I didn't need to instrument the process at all. All I needed was to have the perf subsystem and Linux working or functional on my system, and that was it. The problem, though, is that there's a 4x overhead to recording performance counters while you're running a process. This was some benchmarking that I had done. I thought maybe if I only used one of the counters that it would be only 2x, but no, if you use any performance counters, it's pretty much 4x across the board. So this here is how long it took to run a very basic function with no perf, and this is with perf counters turned on. So there are downsides to this. If you spend a lot of time in the target process, this will have a much bigger impact than our trivial targets, which spend just a very, very small fraction of their time actually running their own code. And yeah, that is the end of this presentation. Did anyone have any questions?
Thank you very much. It was very cool, super interesting. I just did like 2 questions to the agenda. The first one was about what basically the best point of creating a snapshot is. So if you have like inputs that's used multiple times in your program, how do you know what are the best like points in the program's execution to take the snapshot?
Yeah, so that's that kind of comes down to knowing the target, right? So it's, let's see, there is a thought that having a one-size-fits-all solution for fuzzing, it's really awesome and gets you off the ground pretty quickly. But targeted fuzzing, where you spend a lot of in-depth time with the target process, you know how it works, you know the code, those do tend to be more successful than just plugging and playing, right? So knowing where to do the snapshot, it would have to be targeted. You could try to figure out where the process spends its most time. Maybe that could work. You could use perf to figure that out. You could look at the functions that have the most time spent in them. But really, if you're looking for bugs, you're not really looking for where does it spend its most time, right? You want to try and leverage or cause the most code in the program to be executed, basically. Or you want, if it's more of a state machine type thing, you want to cover all the different possible state transitions, right? Yeah, so there isn't an easy answer to that.
Yeah. The second question is about that was just something I think I read in a paper a while ago. There was I have to dig it up somewhere, the link somewhere, but you were storing the state of a process by using like fork calls. So they were forking a process, which basically like creates essentially like you have like the memory mappings and everything available in the child process, and then they were like running it, and if it failed, they were restoring the parent process. So they were basically using fork calls to create like the copy of a parent process. And I was wondering if this could be also useful for fuzzing, or if this is something that wouldn't be, I
So
mean, if you have access to the source code and if you could inject fork calls into the source.
So
But
that is actually a method that a lot of the fuzzers use, is to fork and use that to track the child process. Um, let's see. I haven't read any comparisons, or I haven't done them myself on fork-based fuzzing versus snapshot. So I'm actually not sure where the performance lies on that. That definitely sounds doable. Sounds cool. All right. I think, did anybody else have questions? No? All right. Then I think we will end the presentation here, and I'll put the recording up after it's done processing. And let's do